And welcome back to the Turdford Network. All right, so if you can't tell from this quick introduction, today's video is about waves. And we're not going to get much into it in terms of like the talking part. All this is going to be is a breakdown on some like basic waveology. So as we look at this basic transverse wave in front of us, I need you to be aware of two things. One, I need you to know what this distance is. This is what we know as lambda, or this is what we refer to as wavelength. And it's the distance between two identical points of a wave. So if you look on here, the idea is this. This point is a crest, this point is a crest. So that length is your wavelength. But now this is what will get somebody. This length should also be the exact same length, because that's also between two identical points. So all wavelength is a measurement between two identical points. Now, one last thing. This measurement, this is what we refer to as amplitude. Now, notice something. If I ask you to measure an amplitude, that is not wanting you to measure that. Amplitude is not from crest to trough. That is not amplitude. Amplitude is actually a measurement of how, if you want like a really sexy definition, it'd look like this. Displacement from the rest position. Oh, no, that's man, this is like Book of Coal over here. I mean, come on. That's giving you two. Now, let's just go ahead and kind of get into the equations that we're going to need. If we're going to work some problems with waves, the two equations. One is this. This is the equation for the speed of a wave. Velocity is equal to lambda f, or wavelength times frequency. And then let's see the other equation we're going to be using. T is equal to 1, and that is the number 1, over frequency. So it's not like some letter. That's literally the number 1 over frequency. I love these for a reason. If you stink at algebra, then you're in luck, because the algebra is pretty simple on that equation. If T is equal to 1 over F, that means algebraically F would be the same as 1 over T. So that makes some pretty convenient math if you're working the problem right there and trying to solve. But anyway, so these are two basic equations we need to get started. And now let's make sure you understand everything. V stands for velocity. And velocity should be measured in meters per second on these problems. Lambda stands for wavelength. And we're going to measure it in meters. F stands for frequency. And if you don't really understand what frequency is, if you're looking at a wave, frequency is basically per second. How many times? Somebody start counting. Are you ready? 1,001. How many waves did I draw in a second? I don't know. That's pretty crappy looking. But maybe like 4 waves in a second there. So frequency is just how many waves are you counting per second? So like this wave would have a very low frequency. There are not many waves per second. Whereas this wave, it's like turbo wave. I'm going to do something. Undo, 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 undo. That looks terrible. But hopefully you're getting, oops, little back one. So hopefully you're getting an idea of what frequency is. It's just like your vibrations per second. And the unit we use is after a guy named Heinrich Hertz. So it's 1 over S, actually. But anyway, but a Hertz. And then one more thing. T is period. And that's just period. It's just how long, if you were to look at a wave, period is just asking you one question. How much time does it take for that one wave to pass? For that one single up and down, how much time does that take? And that's all a period is. Now, this is all we need. So let's get into actually working a couple of problems here. So as we take a look at this point, let's try and read this one. This one, let's read what this one's gave us. If the wavelength is, so this problem's given us a wavelength, so there's lambda. Now it says the wave has a frequency of 0.65. So there's my frequency at this point. So as we look at this problem, it's given us wavelength and it's given us frequency. And it says, what is the speed? Well, that's great because we've got an equation that says V is equal to lambda F. So all we've got to do in this problem is V equals 2.3 times 10 to the 4 times the frequency, which is 0.65. And all we have to do now, let's see if I can find my Casio FX115, 2.3, 10 to the 4 times 0.065 hertz. Now, what does this tell you about the wave, this 0.65? That tells you that it's not a whole lot of waves per second taking place. This is a very low frequency wave. So our answer is 1,495 meters per second. And that is our answer to this first example. Well, let's go on and see if we can't do another example. Here's a question about a dog whistle. And it says that dog whistles produce sound somewhere in this range. And that's well above our hearing. So anyway, so here it says that a whistle produces a sound with a frequency. It says a frequency of 25 kilohertz. So there's our frequency. And then it says, what is the sound's wavelength? Assume the speed of sound in air to be 331, which would be a speed, but it also means it's 0 degrees Celsius outside. Anyway, so there's my V, and it's giving me an F, and it's one lambda. Well, once again, this is a great question. V is equal to lambda F, and V is 331 equals lambda times F. I did one thing in this problem, though, that you've got to correct, and that's that K for kilo times 10 to the third. So I've got to correct that and write 25 times 10 to the third, or 25,000 hertz. I can't use the 25 kilohertz. So now all I've got to do mathematically, divide both sides by 25,000. Now let's see if I can pull out my Casio FX115 calculator and do that one. 331 divided by 25,000, and that's equal to, lo and behold, 331. Let's see if we can reduce that. 0.013, and this would be 0.013. Wavelength is in meters, so let's put a box around that one. All right. So one more question. A drum is struck, producing a wave with a wavelength of 110 centimeters with a speed of 2.42 times 10 to the 4 meters per second. So this is a wavelength. It's giving us a velocity or a speed, but it's asking us to find period. So that's how long it takes for the wave to do a single oscillation. So let's see if we can do this. Well, we know that period is equal to 1 over F. Now let's come back and, well, it didn't give us frequency. Hey, wait a second, but it gave us all this other stuff. So V is equal to lambda times F. So V is 2.42 times 10 to the 4. That's equal to a wavelength. Now, that's my V. Wavelength, though, I've done something. I've given you centimeters. Well, let's see. There's 110 centimeters. Well, there's 100 centimeters per meter, so that's pretty easy math. So that's going to be 110 divided by 100, so that is 1.1 meters for a wavelength. So all I'm going to do is 1.1. That's my new wavelength. And let's put that in the calculator. So I want to divide both sides by 1.1 to get rid of it. So 2.42 10 to the 4 divided by 1.1 equals 22,000. 22,000 Hz is what we've got. So there's our frequency. But that's just it. That's our frequency. And this problem asks you to find period. But that's okay. All we've got to do is substitute that 22,000 back into that equation. So we end up with 1 over 22,000. And let's plug that in our calculator. So 1 divided by 22,000 is point 4 zeros and a 4 5. So 0.00004 and this is the time for one oscillation. So we'll put second for a unit on that, and there is our answer to that one. Now, I'll take this opportunity to go back, and if I can think of anything to like give you some tricks on if you're doing my homework for class, pay attention to units. Like I know one of the problems in the homework, I gave you megahertz. Well, that's no big deal. You see the hertz, so you know that that's a frequency. So that's a frequency, but I gave you mega. Well, if you remember, kilo means 1,000, 10 to the third. Mega just means 10 to the 6 million. So if I give you a frequency of 100 megahertz, it's just telling you your frequency is 100 million hertz. And that's all you'd have to do to work that problem. That would be a trick. I'm trying to sit here and think if there's anything else. One, the problem gives you like 2 different frequencies in the problem. And all I want you to do in it is you just work the problem twice. You use it once, I think one frequency is like 42 or something. I don't remember the other one, but you just work the problem twice is all you have to do in that one. So that's no big deal. The only other question, and I'm not going to say too much about it, there's a question about, oh, I love this, a tugboat. So here's my tugboat, and this tugboat's out in the water, and there's danger ahead. So here's like a big mountain up ahead. So this tugboat lets out a little tug. That don't make sense. Lets out a little, lets out a horn. So here comes this tugboat question. It's an echo question. So here it lets out this echo. And then all of a sudden the echo hits the mountain and this echo bounces back. And I think it says in the problem that it takes 2.6 seconds to hear the echo. I think it even gives you a velocity for the wave. And all the question is wanting to know is this: how far is it to danger? By the way, if you were driving a tugboat, this would probably be a very good thing to actually know. So I hope you figure it out, because it'd be a shame to wreck your tugboat. Anyway, y'all have a great day, pleasant tomorrow, and remember, don't eat yellow snow. I don't know, I'm running out of material. Bye.